Hello everyone, let's continue in chapter 16, looking at the definition of curl. So F is a vector field, 3D, so X, Y, Z, and we're defining the concept of curl. So curl F, you can treat it like del cross F. So if you recall, back here, here's 16.2 continued. The del operator, and I put a little vector here to remind us that it's in that vector form, and you're doing you can treat it like an operation. So if you do a cross product and treat it like a vector, then you get this. So that cross product would be the determinant of ijk, like this, and then you put in those partials. So it would be partial respect to x, partial respect to y, partial respect to z of the m, n, and p. So this is m, n, and p. And so that's how you would remember it, although you can write them down, of course, or if it's online, you just look it up. But that is equal to, and then let's go ahead and calculate it. You do this and this, so it's I, and then that determinant, etc. So I'll just write it out. So you get partial p respect to y minus partial n respect to zi minus partial p respect to x minus partial m respect to z j plus partial m respect to x minus, no, I messed it up. That's n right there. N, I'm just copying, I'm not going through it. And then partial m with respect to y, k. Okay, so you can do that determinant yourself and see that that's, of course, what it is. All right, so that will describe later what it means, but it is used right now to determine if a vector field is conservative or not. This is for 3D. All right, so let's take a look at that theorem. So theorem for test of conservative vector fields. All right, so this is test in 3D. So test for conservative vector fields in 3 dimensions, in 3D. Okay. So capital F is conservative. And every time you hear that, you think like conservation of energy, like gravity. That's the one I always picture. So F is conservative if and only if curl F is equal to 0. And it's a 0 vector. So remember, conservative vector field definition is that there exists a potential function that I showed you. But F is, so this is how to test it. You just do the curl of it. All right, so let's look at an example. So the basic process will go determine if the function is conservative, the vector field, and then find the potential function. So that's usually how it's asked, or how I would ask it. So determine sorry, I was looking up something to make sure it's recording. Determine if capital F of x, y, z equal to sine y I minus x cosine y j plus k is conservative, all right, so then later it'd be like, and find the potential function, but we're not doing that yet. I don't know if I wanted you to do it on that one. No, we'll do a different one. All right, so let's calculate. So you can do this now, do it on your own. Calculate the curl of f. It's pretty much a straight up calculation. All right, and then let's go ahead and try it. So curl f, and I usually write curl f. I don't usually like to write the del cross because I'm thinking curl. And it does have to do with like twisting motion locally. It's physics is somewhat complicated, but we'll look at just the basic concept of it. So curl of f, and then you write out the determinant of and put in those values or the functions. So the determinant of I, j, k, and then you put in the partials, partial respect to x, partial respect to y, partial respect to z, and then you put in your functions. So it is sine x is m, sine y is m, negative x cosine y is n, and just 1 is your p. And then you calculate that. So one way to do this is you take the partials as you do the calculation. So when you're doing this, you do the partial and then you write it down. So that's how I like to look. So you're calculating it as you go. Usually works pretty good. So you get 0i minus, and then that's another 0 because it's just x and y in it. So it's 0j plus, and then you get, so that was the next one. So the last one is partial in respect to, so it's going across like this. And that one does have a derivative. So it's negative x cosine y. And then you get minus cosine, and I'm running out of room, of course. I think my writing in my notes are smaller or something. Not sure what it is. All right, let me erase that. Let's try that again. Okay, so I'm looking back, partial of negative x cosine y with respect to x. That's just negative cosine y because derivative of x is 1. All right. So that's, I put in parentheses, so minus cosine y. And then now derivative of sine is cosine. So it's a minus cosine y. K. And everything's 0, and you just add it up, and you get something non-zero. So you get minus 2 cosine y k. So that is not equal to the 0 vector. Therefore, what is your conclusion? Therefore, capital F is not conservative. Okay, so that's the idea. Next, let's look at another definition, another operation. Okay, so the next definition is called divergence. So let me write this like this. So definition of divergence. So let f of x, y, z equal to mi plus nj plus pk. So there's our vector field. And then we'll calculate the divergence, just div of f. And this is what I was thinking earlier, and I apologize. This is your del dot capital F. This is a dot product. So that you treat like a dot product. The other one was just the gradient, which we've done before, but this one is like a dot product. So that is partial m with respect to x plus partial n with respect to y plus partial p with respect to z. So if you did this dot product, I guess I'll just show you. So you would have partial respect to x, partial respect to y, partial respect to z, dot, and then that is just m, n, and p. And then if you do the dot product, you do that partial, and then you right there, and then you add. Remember, it's a dot product, so you add the next one, and then the next one, etc. So it's a calculation. It's pretty straightforward. It's a little easier than curl. And it's used, I'm just presenting it now because we will use it later for one of the theorems. I believe it's the divergence theorem, which you end up doing that calculation. Okay, so a lot of little details in the book, so just try to follow along with all my notes. Let's continue now in 16, chapter 16, or on vector fields if it happens to be a different book. So we need to look at an example of this. We talked about curl. Divergence we'll do later. That's just, I wanted to put it here so that we have it when it's defined. This is kind of like just, these are operations on vector fields. This is another one. So let's continue now and do this example. So this will be what I had mentioned. If you saw the other video, show that the function is conservative by taking the curl and then find the potential function. That would be the typical question, like on the final exam. So show that capital F of x, is this working all right? Yeah. Of x, y, z, hold on a second. Okay. Of x, y, z equal to y squared cosine x 2y sine x plus e to the 2z 2y e to the 2z is conservative. Then find the potential function, and I'll write it out how you'd say it. Find f. Oops, I wrote that twice. Let's try that again. Find f such that del f equals capital F. I'll put in the vector forms. And that is the potential function. So, good spot to do this on your own. Pause it and take the curl of that and show that it's 0. So curl f equal to, and then I like to write this all the way out. I leave space, j and k, like a lot of space this time. And then it's partial with respect to x, partial with respect to y, partial with respect to z. And then now you're putting in your functions, m y squared cosine x, 2y sine x, plus e to the 2z, and move these over. 2y e to the 2z. We're taking the curl of that, and you can see here when you do this partial, like that's just 0, it's gone. Okay, so things like that will happen, make it a little simpler. So it's equal to, and so you usually you go ahead and do the partial as you take the curl of it, the determinant of that. So it's partial respect to y, so it's just 2 e to the 2z, so you get 2e to the 2z minus 2e to the 2z, which is 0, I minus, and then now the middle one, right? And let's do this just for fun. So you're crossing off on the middle one, you're basically doing you're doing this, and then you're doing that determinant. So that is 0 minus 0 because those other variables aren't even in there. So it's 0 minus 0, and then it's ij. And then same idea, cross that one and that one. And for x, that'll be just cosine 2y. So then you get a plus. You get 2y cosine x minus 2y cosine x. Okay, so these are all zeros. 0, 0, 0, which ends up being the 0 vector. Therefore, capital F is conservative, and there exists f such that the gradient of f is equal to capital F. So this is like basically trying to find a function whose derivative is capital F. Well, that's like differential equations. You're integrating to go backwards. And so I have a process to do this. And the way I show this is usually a little different than the book. One of the few instances that I do that, and I believe works much better. So you basically do the partials of each, or I'm sorry, the antiderivatives of each, and then you just compare, and you just say, well, it has to be these functions. And it's none of this, do the partial, then a derivative, and then there's a whole weird process that the book does, and I don't think it's a very good one, frankly. All right, so now find the potential function for f. So what we have then is partial fx equals, and let me get rid of the tape there. Partial fx is this first one, partial fy is this one, partial fz is this one. So you write those out. Partial fx is y squared cosine x. Partial fy is 2y sine x, not cosine, 2y sine x plus e to the 2z, and partial fz is just the 2y e to the 2z. I'm feeling an e to the 2z in our future. I'm just saying. So then you say f of x, y, z, which is what we're looking for, has to equal the integral of partial fx dx. I mean, so you basically do each one of these 3 times. Fx, fy, fz, and then you essentially compare to see which one needs to be what. I'll show you what I mean. So now you're doing antiderivative y squared cosine x dx. You'll do something very similar in differential equations, which I think almost everybody needs to do. And the process will be exactly like this. So it'll be nice to kind of have a head start on it. I'm not sure if this is covered all the time in Calc 3. It needs to be. It should be. I'm just saying, and who knows. So now you do those partials, and you get y squared sine x. Then you say, this is the key part, some function, I'll call it a c, of yz. So there's some function of the other 2 variables. So this is a function of x when you do that antiderivative, but then there could have been other functions of the different variables than x, and those would zero out when you do the partial. Let's do the next one. Partial f x y z equal to antiderivative partial fx fy dy. So you integrate all of that. So that's the 2y sine x plus e to the 2z dy. And when you get that, it's going to be y squared sine x, which is the same one just above. See that? Plus ye to the 2z. And then you say plus some function of x, z. That's those other 2 different variables. So right now, we can see that we have this function is the same. Okay, so you don't repeat the functions. It's those. That's the same thing. Okay, let's do the next one. fxyz equal to the integral of 2ye to the 2z, 2ye to the 2z. And looks like that's all that's going to be is y to the 2z, right? So that's just y e to the 2z. Y squared. No, that's right. Y squared. Wait, I did something wrong. No, that's it. It's that 2 because you're doing the partial z. Yeah, no, that makes sense. Before it was, if this is just a constant, you get y back with respect to y. Since this is with respect to z, you have to do that chain rule on the 2z. So this is it. Then that's some function of xy plus some function of xy. And so we can see here that the y to the 2z is this one. I always like to take the sign with it because its sign matters there. So that's your function, and then you do say plus a constant. So you just put those pieces together. And you can always check it by doing the partials or the gradient and see if you get f. That's all you really have to do in the end. So thus, f of x, y, z is equal to y squared sine x plus y e to the 2z. And you do say plus some arbitrary constant. So you take each of the partials, integrals of each one with respect to each variable, and you just compare it. That's all you have to do. Don't repeat the function. And then you can test by just doing the gradient of f and see if you get capital F. So that del operator is really the gradient. That's really all that means. All right, so, and if you test that, you get, again, your capital F would be your y. So you can do it now if you want to do. Partial f, so it's y squared cosine x, 2y sine x, and then that's just 1, so you get e to the 2z. And with respect to z, you just get 2y e to the 2z. So everything checks out. So you can check it that way. So this is a very typical question right here. Put a star next to it, which means a typical question that might show up on an exam. And it does come up in differential equations later, that exact same form. It's presented a little differently, not for vector fields, but the process is the same.